Hello children, good morning. In the previous class, you have studied about momentum, second law of motion and problems related to second law of motion. Then what is momentum? The momentum is nothing but the product of the mass and velocity of a body. The momentum is denoted by the symbol P and the mathematical expression of the momentum is given by P is equal to m into V. And the SI unit of momentum, the SI unit of mass is kg and the SI unit of velocity is meter per second. So, the SI unit of momentum is kg meter per second. P is equal to mv. So, the momentum is equal to the product of the mass and velocity of the body. So, the momentum is directly proportional to mass of the body and also the velocity of the body. It means if the mass and velocity of the body increases, the momentum increases. If the mass and velocity decreases, and the momentum is also decreases. Therefore, the momentum mass graph and momentum velocity graph is a straight line. Next, Newton's second law of motion. It states that the rate of change of momentum of a body is directly proportional to the unbalanced force acting on the body, and the change in momentum takes place in the direction of unbalanced force. The rate of change of momentum is directly proportional to the unbalanced force. So we can write it as F is proportional to dp by dt. Here F represents the unbalanced force acting on the object and dp represents the rate of change of momentum and dt represents the time taken for this change in momentum. So, the unbalanced force acting on the object is directly proportional to the rate of change of momentum. If the rate of change of momentum is less, then the force acting on the object is less. If the rate of change of momentum is more, then the unbalanced force acting on the object is more. And the force is inversely proportional to dt. It means the time taken for the change in momentum is less, then the force acting on the object is more. Then if the time taken for the change in momentum is more, then the force acting on the object is less. So, F is proportional to dp by dt. In today's class, we will learn about Newton's second law of motion and law of conservation of momentum. Now, let us know about Newton's third law of motion. From Newton's first law, we learnt what force is, and the Newton's second law gave us a measure of force. And the Newton's third law of motion tells us about the nature of the force. According to this law, when an object A exerts a force F2 on another object B, then the object B also exerts some force F1 on the object B at the same instant. These two forces are always equal in magnitude but opposite in direction. The two opposing forces are also known as the forces of action and reaction. The two forces of action and reaction act on two different objects A and B. They never act on the same object. Therefore, the third law of motion tells us that when two objects interact with each other, there exists a pair of equal and opposite forces. So, Newton's third law of motion states that to every action there is an equal and opposite reaction. Next, let us know about some of the applications of Newton's third law of motion. Some of our day-to-day observations can be explained in terms of Newton's third law of motion. Let us take an example of walking. To walk on the ground, we push the ground backwards with our foot. This push is known as action. As a reaction, the ground pushes our foot forward with the same force. Because of this forward reaction force of the ground, we are able to walk in the forward direction. Next, another example is swimming. While swimming, a swimmer pushes the water backwards with his hands and feet. This is a force of action. The water pushes the swimmer forward with the same force of reaction. Another example, when a person jumps out of a boat, he pushes the boat in the backward direction. The boat exerts an equal force on the person in the forward direction. So, when the person jumps out of the boat moves backward. Now, let us know about the law of conservation of momentum. It states that if a group of bodies interact with each other, their total momentum before and after the interaction remains constant, provided no external force is applied on these bodies. This law can also be stated as the total momentum of a system remains constant if no net external unbalanced force acts on the system. It means momentum of a system is constant if net external force acting on it is zero. For example, consider a moving ball and a stationary ball. Let a moving ball collides with stationary ball lying on the ground. After collision, the moving ball will slow down. It means its velocity decreases after colliding with the stationary ball. On the other hand, the stationary ball begins to move. It means its velocity increases after the collision. We know the momentum of a body is equal to the product of the mass of the body and the velocity of the body. So it is given by P is equal to m into v. You know, the momentum is directly proportional to velocity of the body. Here, when the moving ball collides with a stationary ball, the velocity of the moving ball decreases and the velocity of the stationary ball increases. It means the momentum of the moving ball decreases and the momentum of the stationary ball increases. It means when two balls collides with each other, the moving ball loses momentum and the stationary ball gains momentum. It means the loss of momentum of one ball is equal to the gain of momentum of another ball. It means the total momentum of these colliding balls before and after the collision remains the same. This is called the law of conservation of momentum. Next, let us know about the mathematical interpretation of law of conservation of momentum. Consider a system consisting of two bodies A and B of masses m1 and m2 moving with initial velocities u1 and u2 respectively. At the time of collision, body A exerts a force F2 on the body B and body B exerts equal and opposite force F1 on body A. Let V1 and V2 be the velocities of the body A and B respectively after collision. Here, the mass of the body A is m1 and velocity is u1. Therefore, the initial momentum of the body A is m1 u1. And The mass of the body B is m2 and its initial velocity is u2. Therefore, the initial momentum of the body B is m2 u2. After collision, the velocity of the body A changes to v1 and the velocity of the body B changes to v2. Therefore, the final momentum of the body A is m1 v1 and the final momentum of the body B is m2 v2. Therefore, the total momentum of the system before collision is m1 u1 plus m2 u2. And the total momentum of the system after collision is m1 v1 plus m2 v2. Next, the rate of change of momentum of the body A is equal to change in momentum of body A by time taken. The change in momentum of body A is equal to the final momentum of body A minus initial momentum of body A. The final momentum of body A is m1 v1 and the initial momentum of the body A is m1 u1. So the change in momentum is m1 v1 minus m1 u1. And the time taken for this change in momentum is t. Therefore, the rate of change of momentum of a body A is equal to m1 v1 minus m1 u1 by t. Next, the rate of change of momentum of body B is equal to change in momentum of body B by time taken. The change in momentum of body B is equal to the final momentum of the body B minus initial momentum of the body B. The final momentum of the body B is m2 v2 and the initial momentum of the body B is m2 u2. So the change in momentum is m2 v2 minus m2 u2. And the time taken for this change in momentum is t. Therefore, the rate of change of momentum of body B is equal to m2 v2 minus m2 u2 by t. Next, according to Newton's second law of motion, force acting on body A is equal to rate of change of momentum of body A. The force acting on the body A is F1 and the rate of change of momentum of body A is m1 v1 minus m1 u1 by t. Consider this as equation 1. And the force acting on body B is equal to rate of change of momentum of body B. The force acting on the body B is F2 and the rate of change of momentum of body B is m2 v2 minus m2 u2 by t. Consider this as equation 2. According to Newton's third law of motion, action F1 is equal and opposite to reaction F2. Therefore, from equation 1 and 2, we get F1 is equal to minus F2. From equation 1, F1 is m1 v1 minus m1 u1 by t, and from equation 2, F2 is m2 v2 minus m2 u2 by t. Here we can cancel the t on both the sides. Next, m1 v1 minus m1 u1 is equal to m2 v2 minus m2 u2. Next, multiply by minus m2 v2 minus into minus plus m2 u2. Next, take minus m2 v2 to left hand side and m1 u1 to right hand side. Then m1 v1 plus m2 v2 is equal to m1 u1 plus m2 u2. Therefore, this shows that total momentum after collision is equal to total momentum before collision. So, this is the law of conservation of momentum. Next, Let us consider the example of recoil of a gun. The bullet inside the gun and the gun itself form a system. Before firing, the gun and the bullet are at rest. Therefore, the momentum of the system before firing is 0. When the bullet is fired, it leaves the gun in the forward direction with certain momentum, and the gun moves backward with a momentum equal to the momentum of the bullet. Therefore, the velocity with which the gun moves backward after firing a bullet is known as recoil velocity. Next, let us calculate the recoil velocity of a gun. Let the mass of the bullet be small m, velocity of the bullet after firing be small letter v, and mass of the gun be capital M, and velocity of the gun after firing be capital letter V. Therefore, the total momentum of the system after firing is capital MV plus small mv. Therefore, the total momentum of the system after firing is equal to the momentum of the gun plus momentum of the bullet. Momentum of the gun is capital MV and momentum of the bullet is small mv. Then, according to law of conservation of momentum, capital MV plus small mv is equal to 0. It means the momentum of the gun plus momentum of the bullet is equal to 0. Next, capital MV is equal to minus small mv. Therefore, capital V is equal to minus mv by capital M. Here, the negative sign shows that the direction of the velocity of the gun after firing is opposite to the direction of the velocity of the bullet. And the recoil velocity of a gun is inversely proportional to its mass. It means V is inversely proportional to capital M. It means if the mass of the gun is less, then the recoil velocity is more. If the mass of the gun is more, then its recoil velocity is less. Therefore, the light guns recoil with large velocity and heavy guns recoil with small velocity.